Hello, welcome to Noise Management and Control. Today is the 4th day of this week, and yesterday we had just started discussion on how do waves travel in a closed tube, a tube which is of constant cross section, finite length, and which is rigidly closed at one of its ends. So, we will very quickly go over the problem formulation. This is the picture of this tube. One end of the tube where x is equal to minus L, the pressure at the other one end of the tube is P minus L t, and that is equal to P1 cosine omega t plus phi. And at the closed end, it is a closed end, so it has some physical implication. We will come to that just in a moment. So, this is the tube, and what we are interested in finding out is pressure at any point in the tube. And the general solution for one dimensional wave equation can be expressed in terms of pressure transmission line equations. So, these are our transmission line equations. This is in the regular form and this is in a matrix form. So, now our aim is to solve these equations so that we know what are the values of P plus, P minus and S, and the moment we know these three entities, we have an expression for pressure at any point in the tube. So, for this we will use our boundary conditions. So, this is boundary condition number 1. So, it is BC1. The other boundary condition is that the tube is closed, and what does that mean? So, at x is equal to 0, so this is x is equal to 0. If you have an air particle at x is suppose this is an air particle just at the closed end, because the tube is rigidly closed, the end of the tube has no freedom to move back and forth, and because of this the particle which is extremely close to it, just next to it, that also cannot move back and forth. So, what that means is that at x is equal to 0, particle velocity u at 0 t is also 0, because the tube is closed, and not only just closed, it is rigidly closed. So, that is why the particle velocity is 0. So, we have two conditions: at x is equal to 0, u is 0, at x is equal to minus L, we know the pressure. So, now with these two things we will figure out what are the values of P plus, P minus and S. So, we again go back to our transmission line equation and we use the second boundary condition. So, second boundary condition says at x is equal to 0, u of 0 t is equal to 0. Okay. So, let us call this equation, the first equation, as 1a, this equation as 1b and this equation as 2. Now, what we do is we calculate u of 0 t from 1a to get. So, we are going to use, oh I am sorry, not 1a, 1b. From equation 1b we calculate the value of u at x is equal to 0. So, u of 0 t is real of P plus by z naught minus P minus by z naught e to the power of s x over c and e to the power of minus s x over c at x is equal to 0, they are 1. So, they do not they go away, and then I have e to the power of s t. Now, so this is 3. So, comparing 2 and 3, comparing 2 and 3, we see that the value of u will be 0 only we infer that P plus equals P minus. Okay. So, using this understanding we rewrite down the transmission line equations. So, we rewrite so here we get P of x t, u of x t and the first constant is P plus and the next constant is P minus, but we just said that P plus equals P minus. So, it gets replaced by P plus by Z naught and minus P plus by Z naught, and then it is E minus S x over C, E S x over C, e to the power of S t. So, now we have eliminated P minus, we still have to figure out the value of P plus and S. So, now we look at the first boundary condition. Boundary condition number 1, what does it say? That pressure at minus L T is equal to P 1 some constant cosine omega t plus phi, and I can write P 1 cosine omega t plus phi as the real component of P 1 e to the power of j omega t plus phi. So, this is again equation 1a, this is equation 1b and this is equation 4. So, this is our equation 4, and then from equation 1a we again calculate what is the value of pressure at minus L. So, from 1a we get P minus L comma T is real of P plus E minus S x over C plus P plus E S x over C e to the power of S t. So, this is 5, and equation 4 and 5 both are the expressions for pressure at minus L, x is equal to minus L. So, equating 4 and 5, what do we get? Real of P 1 E j omega t E j phi is equal to real of P plus E. So, I am going to put x is equal to minus L here. So, it will be E S L over C plus P minus E minus S L over C e to the power of S t. So, this is equation 6. Now, once again equation 6 is valid at all times and for all S. It is valid for all S and for all times. So, that can be true only if the time component here, which is this, is same as the time component here, and simultaneously the other component this other component should be equal to this other component simultaneously. Both these equations should equalities should hold. So, if that is the case, so from this we get that S t equals j omega t, which tells us that S equals j omega. Okay. So, this is from the equalities of terms in red, and then once we substitute it, then we get the other equalities P 1 E j phi equals P plus, and now I am going to substitute instead of S the value of j omega. So, E j omega L over C plus E minus j omega L over C, this thing. Okay. So, this is I am getting because I am equating terms indicated in orange. Okay. Now, we know that e to the power of j omega L plus e to the power of minus j omega L over C is nothing but 2 cosine omega L over C. So, I get from here P 1 E j phi equals P plus twice cosine omega L over C. So, P plus equals P 1 by 2 E j phi into 1 by cosine omega L over C. So, this is my P plus. My P minus we had already calculated, and that is equal to same as P plus. So, this is the second thing, and S we have figured out is equal to j omega. Okay. So, these are equations 7. So, once we have these equalities, I can put equation 7 back into equation 1a and 1b. So, that is what I am going to do. So, putting 7 in 1a and 1b, we get, what do we get? We get transmission line equations for pressure and velocity in specific terms. So, my equation for pressure P of x t is real of P plus, and P plus is what? This complicated thing. So, it is P 1 E j phi by 2 cosine omega L over C, and in parenthesis I get E minus j omega x over C plus E j omega x over C times E j omega t. So, this is my equation for pressure, and I know that this is what? Cosine omega x over C times 2. So, my modified equation of pressure becomes, or my transformed equation becomes P 1 E j phi by cosine omega L over C, and this 2 term cancels out this 2 term. So, I get cosine omega x over C E j omega t, and I manipulate this further and I get P 1 by cosine omega L over C cosine omega x over C E j omega t plus phi. So, my pressure relation becomes, so if I take the real power portion of this, this is the only complex portion, exponent to j omega t plus phi, and its real portion is cosine omega t plus phi. So, P of x and t is what? P 1 divided by cosine omega L over C, cosine omega x over C, cosine omega t plus phi. So, this is the expression for pressure, and this expression, using this expression I can calculate the values of pressure at all the points in this tube, at all the locations in this tube, and I know P1 because that number is given to me. So, this is the expression for pressure, and now what we will do is we will develop an expression for velocity. So, for expression for pressure we had used equation 1a, now we will develop an expression for velocity. So, we will do that. So, for velocity we use 1b. So, my expression for velocity is u x t equals real of p plus by z naught e minus j omega x over c, okay, minus e j omega x over c e j omega t. And now what we are going to do is we are going to put this thing as the value of p plus, okay. So, this is real of p1 e j phi divided by 2 cosine omega L over c, that is my p plus, and we also know that E minus j omega x over c minus E j omega x over c, if I take their real and imaginary components and subtract one from other, I get cosine omega x over c minus j sine omega x over c minus cosine omega x over c minus j sine omega x over c, right. So, what I end up is these two cancel out, I get minus 2j sine omega x over c. This is what I get. So, this thing is nothing but minus 2j sine omega x over c e j omega t, and there is also a z naught here. So, I can take all the real terms outside the bracket. So, it is p1 by, and then this 2 cancel out. So, what I am left with is cosine omega L over c times z naught real of minus j sine omega x over c, and I have E j omega t plus phi, and this is equal to P1 divided by cosine omega L over c z naught real of minus j sine omega x over c, and this thing is cosine omega t plus phi plus j sine omega t plus phi. So, if I take the real portion of this, what I am left with is I have to multiply j by j, I get minus 1, and then there is also this negative 1, negative already there. So, what I get is P1 by cosine omega L over c z naught times sine omega x by c sine omega t plus phi. Okay. So, this is my velocity. So, eventually let us summarize. The expression for pressure is P1 by cosine omega L over C times cosine omega x over C times cosine omega t plus phi, and velocity is P1 divided by z naught cosine omega L over C sine omega x over C sine omega t plus phi. So, these are the expressions for pressure and velocity in a tube as shown here, which is a closed tube, rigidly closed tube, and the pressure at x is equal to minus L, which is the open end, is defined by P1 cosine omega t plus phi. This is the, so if I use these boundary conditions and the transmission line equations, and if I patiently run through all the mathematics, I can actually predict pressure and particle velocity at all the points in this system, at all the points in the system. So, this is important to understand. Now, let us look at these equations a little bit more carefully, but before we look at this set of equations, we find what does, so this is the equation we got from equation 1a, okay. And when we look at this entire thing, this green box, what does it represent? This represents complex pressure amplitude, because when you go back to our original definition of complex pressure amplitude, we had expressed it in three forms. So, this is where we had, so there is this term e to the power of st, and whatever is multiplied to e to the power of st, everything else goes into complex pressure amplitude, right, everything. If you just remove e to the power of st, whatever you are left with is the complex pressure amplitude of the wave. Similarly, complex velocity amplitude of the wave in if we look at form 3 is also shown here. So, now we go back this expression, right, here it is real of some complicated expression multiplied by e to the power of j omega t, and we know that s is equal to j omega in our case. So, if I remove e to the power of st from here, whatever I am left with is the complex pressure amplitude, which is p x omega, okay. So, p x omega is this thing, and what does that mean? P x omega is same as this thing. I mean, of course, this is the real portion of it, if this is the real portion of it. Similarly, the complex velocity amplitude for velocity wave is this entire thing. Complex velocity amplitude is this thing, u x omega, okay. And so, we will just make a small box here. So, p x omega is what? Is equal to p1 e j phi divided by 2 cosine omega L over C times this entire thing is 2 cosine omega x by C, right. And complex velocity amplitude u x omega is equal to p1 e j phi divided by z naught 2 cosine omega L by C, and what else? And then of course, I have to multiply by minus 2j sin omega x over c, this thing. Okay. So, if I have to compute the specific characteristic impedance of this system, then specific specific acoustic impedance of this system, that is a function of Pxw and Uxw. So, that is equal to Px omega over Ux omega, and if you do the mathematics, what you find is P1 Ej phi 2 cos omega L over C, they all cancel out. Essentially what you end up getting is Z naught j cotangent omega x over C, and of course, there is a negative sign. For this system, the complex the specific acoustic impedance of this system, which is a tube with rigidly closed end, Z is equal to minus j Z naught cotangent omega L over C. This is how we calculated it, right? This is what we calculated. So, I am just rewriting it later. This is omega x over C. And if I just plot this thing Z x omega divided by minus j Z naught. So, I am left with cotangent omega x over C. Okay. So, if I plot this on xy plane, and on the x axis, let us say I am plotting omega x over C. So, either I can increase my omega or I can increase x, and on the y axis, let us call this function Zn. So, it is basically cotangent of omega x over C, normalized Z, that is why I am calling it, and let us say that this is pi over 2 pi 3 pi over 2 2 pi and so on and so forth. Then at x is equal to 0, Zn is infinite, and at, so we will actually just plot this function. So, at x is equal to 0, cotangent omega x over C is infinite. At x is equal to pi over 2, tangent of pi over 2 is infinite. So, this number will become 1 over infinity, that is 0. So, my function, it will look something like this. And this pattern is going to repeat, okay, over a period of 2 pi. So, the specific acoustic impedance in the tube, it varies in this type of thing. So, for a given frequency, this is my x is equal to 0. As I am moving in this direction, okay, as I am moving in this direction, initially the specific acoustic impedance will be infinite, because x is equal to 0 here, and as I move in here, it starts dropping and gradually becomes 0, then it starts approaching negative infinity, and it just keeps on repeating this cycle. So, in this case, so this is how specific acoustic impedance changes. So, this is one part of the problem which I wanted to discuss. Tomorrow we will continue this discussion on closed tubes, and specifically we will discuss these two equations and relate them to this concept of standing waves or standing waves. So, with that we close the discussion for today, and we will meet once again tomorrow. Thank you. Bye.